We're pleased to have Zhao Song here to give the talk today. Zhao is a graduate of this department. He graduated 2 years ago. And since then he's been, as you can see, a postdoc at Princeton and IAS. He had a really remarkable collection of results as a PhD student, and it's continued on as a really remarkable collection of results. And so today he's going to be giving an overview of all of that. And this is a practice job talk, basically. Zhao is on the job market for faculty positions. And so if you have any comments about the talk, please do let him know. I'm sure that would be helpful. And then after the talk, we're going to have a gather town, just like every week, which I believe when we put on the chat, closer to the end of the talk. So without further ado, Zhao.
Hello, everyone. Today, I'm going to talk about optimization from linear programming to deep learning. I will first give you an overview of my research. Over my PhD time, I have done research in both theory and machine learning. In theory, I'm very interested in designing fast algorithms. And over the last couple of years, I was working on improving the running time of many fundamental algorithms. Many of them are named as top 10 algorithms in the 20th century. For example, linear programming, fast Fourier transform, fast multiple method, and matrix factorization. In addition to that, I'm also interested in applied math. I'm especially interested in probability. For example, proving concentration in inequalities. So as all of you know, that the turn-off bound is a fundamental tool in theoretical computer science, where almost every randomized algorithm papers require that. Over the last few decades, many of the research questions in computer science rely on analysis of matrix turn-off bound. I spent a lot of time to prove several new matrix turn-off bounds over my PhD. On the machine learning side, I'm mainly focused on building the theory behind the modern machine learning method, especially some non-convex model, such as deep learning. I was trying to build a deep learning theory from several perspectives. First, why SGD is working for deep learning, and how fast can we train a neural network, and also what is the private way of training neural networks. Over my postdoc time, I'm putting a lot of effort to actually implement ideas I learned, created, invented over my PhD time to build some practical machine learning systems from several perspectives. Under the guidance of system professor Kelly at Princeton, I would done system type research in two directions. The first one is making the deep learning training more secure while using some TCS ideas. And our private machine learning system, InstaHeight and TextHeight, recently won the Bell Lab Prize. The second one is to speed up the training of neural network using some TCS idea scan, especially based on LP techniques. And in order to build these two systems, and many of the ideas come from my theoretical computer science papers. So today's talk is going to have three parts. The first part, I'm going to tell you the motivation and several key tools we are going to use for LTP and deep learning. And second part, I will focus on linear programming. And last part, I will focus on deep learning. So what is optimization? Optimization can be either non-convex or convex. Usually, you give a function, and your goal is to find some primary W, such that f of W is minimized. So what do we do in general? So first, we choose some random initial point for W0. And then actually each step, we just do a gradient type of algorithm. So usually, the optimization method consists of two parts. The first part is number of iterations. And the second part is the cost per iteration. Usually, the cost per iteration has to be at least the input side of the problem. So naively, in order to implement the optimization algorithm, and it takes at least t times c time. And however, the question is, can we do actually better? So the point is that possible just to read the input of the problem once, and then like each iteration span the sublinear of input side? Ideally, if your t times the small of c is much smaller than c, then you can hope to get some time, which is just the input side of the problem. And the major observation we use in a couple of papers presented in this talk is something called WT changes very slowly. On the other hand, you can think about delta WT is a possibly sparse or low rank. Therefore, we can try some compression idea, for example, sampling or sketching to speed up. Optimization have two categories. One category is called convex optimization. So linear programming is one of the most repetitive case. And usually you give a matrix and several vectors, you want to minimize the linear equations such make sure some linear constant also holding. So LP, so there are thousand problems in practice, also in theory can be written as LP. For example, energy industry, transportation system, food and agriculture, efficient manufacturing, and also bipolar matching and max flow. LP is named as one of the top 10 algorithms in the 20th century. And another big category called non-convex optimization. The most repetitive example is called deep learning. So where you give a bunch of data, x1 to y, x1 to xn, and also their corresponding labels. You want some fun weight matrix A to minimize this objective function. Also on the current Earth, there are some problems that can be solved at deep nets. And of course, this could be one of the very important algorithms in this century. One of the part of my research is trying to focus on improve the powerful hammers, because one way of doing research is you can use the powerful hammer to solve your problem. So LP is of course one of the important powerful hammers of the last century, and deep learning is the most powerful hammer in this century. Part of my research is focusing on making those hammers better and better. Today, the first of our talk, I will explain some techniques like the observation, the weights change slowly, and also some techniques called sketching and streaming. And using these techniques, we can design some fast solver for a very fundamental problem in the field of optimization, for example, linear programming. In the second half of our talk, I will show how to generalize those techniques from the LP to our current neural network training. I will first share my research themes in deep learning, and then I will focus on one part of my deep learning research, for example, how to speak out the training neural network in both theory and practice. Let me start with some tools. So the first tool is called slowly changing, and the second one is called sketching. I will first explain what's the meaning of slowly changing here. So in reality, and when you are taking care of dogs and they are playing in the garden, and most of the time, like your dog, they are doing some nonsense move. And in this case, humans don't need to move at all. And also, when you are trying to take care of your kids while COVID-19, and your kids are playing in the garden, usually with the adults, they are just sitting at their own location by rotating their eyes and do not make any move at all. So in order to take care of this slowly changing, the major idea is called lazy, which you can see from both pictures. So here I will give you an example what does slowly changing mean in deep learning. So in practical deep learning, if you plug the weights between two iterations, you can observe they are small. And in deep learning theory, you actually need this thing implicitly. For example, in the bottom picture, this is a one hidden layer neural network. The input layer is have D, which is number of pixels in the images, and M here for the hidden layer is the number of neurons. And the last layer, usually for MNIST, we have 10 nodes. And in my toy example, there is only one node. And if you output 1, it means you are trying to figure out a dog. Otherwise, if -1 is a cat. And on the left hand side, there is the input picture. So usually deep learning has something called activity function, which is ReLU. And here we see a neuron, for example, the first node in the hidden layer, and you look at all the weights from the input layer connected to this first node, and then pass this input output to a ReLU activity function. Here W is your weight and X is one image. And we think a neuron is fire if the input product between weight and the image is positive. and we say non-fair if it is negative. So the major observation we have in the deep learning theory, and we do need it, which is the number of neurons that change status over all iterations are very tiny. So the change state means you want to change the state from fire to non-fire or from non-fire to fire. In this picture, the dark green one means fire and the light green one means on fire. And this is the first iteration. And in second iteration, the node 3 it flipped. And in the next iteration, the node M flipped. This is the illustration what I mean by neurons, they are changed very slowly. The next tool I'm going to plan is called sketching. So what is sketching? If you Google this word, and it usually means the following. If I give you a picture, and you just draw the boundary of this person, and of course you lose a lot of information. For example, a color and some details. And however, even you lose those informations, and you can still tell who is this person based on a right-hand sketch picture. So in numerical linear algebra, sketching has some particular math meaning. This idea was originally from Zhao's paper and Ken Clark and Woodruff paper, and then Woodruff read a survey book. It lists a lot of applications of sketching. Usually, the sketching also referred to be a word called sketch and solve. And where you give here example, I give you a matrix A, which is a very tall matrix, and also the correspondence vector B. And your goal is going to find some x such that AX is roughly equal to B. And mathematically, you can do a L2 version where you just look at L2 norm of AX minus B. Of course, you can also look at L1 norm or other LP norm. So here I'm just focused on L2 norm. So say you have a L2 regression solver A, and you can solve this L2 regression question. And now what you need to do is you are going to choose a sketching matrix S, which only have very small number of rows. Here you are thinking of an over-constrained regression question where N is much bigger than D. And say your S has size some poly D times poly log N. So what we need to argue is the solution to the AX equal to B is actually, the solution to the SAX equal to B is actually a good solution to AX equal to B, a reverse order, And therefore, you can just run a solver on the small version of the problem, which is input is SA and SB. One important remark here is this sketch and solve idea, we never modify the solver. We just use a sketching matrix to do the dimensionality reduction. Sketching techniques has a lot of applications. And for example, sketch solve, we can use to improve many fundamental questions in numerical linear algebra. For example, linear regression, low-rank approximation, and also other general version of low-rank approximation. And however, all the previous works, they are really just based on sketch and solve, where you only use sketching once to do a dimensionality reduction, and you never modify a solver. Today, I'm going to implement some idea which was developed by me and my co-authors over my PhD time. It's called iterating and sketching. In this case, we need to modify the solver. And I will give you some examples how powerful is new techniques. For example, linear programming. And furthermore, and you can show this technique can be used for some other complex setting. For example, cutting plane method. Most surprisingly, this idea also can be used for non-convex method, which is deep learning. And on one hand, we can show this idea can be used to speed up the training time of the deep learning neural network in theory. And on the other hand, in an Euclidean summation, and we have some experiments can show the LP ideas can be used to speed up neural network training in practice. Now, let me go to the second part of the talk. I will talk about linear programming. Let me remind you what is a linear program. So in linear program, you are given a matrix A and a vector B, and they are going to corresponding to a convex region in the 2 dimension. Now, suppose I give a vector C, which is length 2 vector. The first entry is +3, and second number is +2. And this vector is going to decide an angle of a line in this 2 dimension. For example, like this. And now what you need to do is you need to push this line until you touch the boundary of this convex region. That's the time where we say we solve LP. So linear program has a very, very long history. The earliest time result mentioned can be dated back to in 200 years ago. The first algorithm for linear programming is called the Simplex Algorithm. This algorithm is developed by George Dantzig in Second World War. This algorithm is very efficient in practice. However, in theory, due to Klein-Mitten cube, this algorithm takes exponential time. Since then, there is a long-standing open question whether we can solve LP in polynomial time. Due to the implicit algorithm by Leonard Kitchen in 1979, this is the first time polynomial time algorithm for linear programming. However, this algorithm is never practical at all. No one uses this algorithm in practice. Therefore, there is another motivation. Can we actually design some LP algorithm which we can analyze in theory, show it can be solved in polynomial time, and also in practice, can we really run it? In 1984, the Eugen Kammerker proposed an algorithm called interior point method. This algorithm also runs in polynomial time and also can be used in practice. So nowadays, when people are trying to solve LP, in some cases, we use simplex algorithm, and in some cases, we use interior point method. So this algorithm is efficient both in theory and practice. And one thing I want to mention is that this algorithm has only root n iterations. However, the elliptic algorithm has to take n iterations. Therefore, there are a lot of follow-up works in order to speed up the LP algorithm. They are majorly focusing on the interior point type of algorithm rather than elliptic algorithm. Since the Vedia 1989 algorithm, the fastest algorithm for dense and full-rank LP algorithm LP remains n to the 2.5 times the bit precision. In 2019, a paper with joint work with Michael Cohen and Inta Lee, and recently this paper got accepted into Journal of ACM. We show that we can solve LP, and by breaking the barrier n to 2.5, our algorithm takes only n to omega plus n to the 2 plus 106 time. Here, the omega is the exponent of matrix multiplication. N to omega is the time for multiplying an n by n matrix with another n by n matrix. Currently, omega is 2.37. However, the community believes that omega could be equal to 2 eventually, because the best lower bound we know for matrix multiplication is only n squared log n due to Ryan-Raz. Here, I would like to justify why our algorithm is optimal in some sense. So currently, even you want to solve a linear system, which is AX equal to B, without this C transpose X, the best algorithm we know has to take n to the omega time. Therefore, n to the omega time is necessary. And for the current omega, the second term, n to the 2 plus 106, is dominated by the n to the omega. So now, however, you may ask a question, what if one day omega equals 2? At that time, linear system will take only n squared time, while LP takes n to the 2 plus 1/6 time. So therefore, it's an open question, and we want to understand whether we can solve LP as fast as linear system. In other words, can we actually improve 1/6 to something else, or completely remove it? The short answer and the quick answer is yes. In a work during my postdoc time with colleges from Columbia, Shunhua Jiang, Omer Winston, and Hengde Zhang, we can improve this 1/6 to 1/18. Here, I will give you a brief history of solving linear system and LP. Solving linear system boils down to improving matrix multiplication. The naive time of matrix multiplication takes n to cube time. The first subqubit time is due to Strawson. And then there is a long time people believe that solving matrix multiplication takes n to 2.5 at least. Due to Cooper-Smith and Wignall tensor, they break this barrier. Then people are still trying to improve the exponent of matrix multiplication. The progress over the last 30 years are very slow. They are almost just 0.001 digits for every paper. For linear program, at the beginning, it takes the exponential time. And then we know it can be done in polynomial time, but we don't know how to make it practical. And due to the interior point method, we can have a practical LP algorithm and also polynomial time in theory. People are trying to improve the LP algorithm. And until the 1989, due to Vidya, and he gave an n to 2.5 time LP algorithm. Over the last 30 years, this algorithm remains unchallenged for the worst case. However, for the special case where the rank of the matrix is small, or the sparsity of the matrix is small, this algorithm can be significantly improved due to Lee Cipher work in 2014 and 2015. In the last year, in a joint work with Cohen Lee, we show that we can actually match the LP algorithm to the linear system algorithm. However, as I mentioned in prior slides, if one day omega becomes 2, LP linear system takes n squared time, however, LP takes n to the 2.16. And in this year work, and we improve this exponent from 0.16 to 0.05. As you can see from this picture, the 0.05 is actually very close to 2. In the next few slides, I will slightly talk about the details of the LP, but just to give you some high-level explanation. So LP solving linear program boils down to an iterating algorithm where you have root n iterations, and each iteration involves several numerical linear algebra calculations. For example, matrix vector multiplication, matrix multiplication, and matrix inverse. Unfortunately, I will not explain why that algorithm suffices to solve LP. Instead, I will just focus on present the computation bottleneck for the algorithm. Here is oversimplified algorithm for LP. At the beginning, I is our counter, we set to 1, and we initialize some vector W. And there are root n iterations, and we compute H based on W, and this step is very cheap. And then we compute P, which is the inverse of A times diagonal of W times A. Here, A is the input constraint matrix of LP. And then we compute a matrix vector multiplication between P and H. And then we update W. And we increase the counter, and that's the algorithm. The naive implementation of this algorithm will take n to the omega plus 1/2. Because this algorithm has root n iterations and n to the omega time per iteration. The cost per iteration is majorly from line 4 and line 5. In line 4, you need to compute the matrix P. This step is going to take n to the omega time. And in line 5, you need to compute the p times h, which is the matrix vector multiplication. This part you also take n squared time. So in Witting's algorithm, he can improve the bottleneck n to the omega to n squared. However, as you can see from this algorithm, there are still like at least 3 locations you need to pay n squared time. Even write down the matrix P in every iteration, it already takes n squared time. So therefore, whether this N2-215 algorithm can be improved has been open for almost 30 years. Here, I would like to briefly tell you what is our techniques. So we need to use some random compression techniques, and for example, sketching. And there are 2 ways of doing sketching. One is sketching is very fast matrix and very dense matrix everywhere. In R, you have a random Gaussian entry. And the second one is you are creating a sampling matrix, which is a diagonal matrix. However, the diagonal terms are only small, only B terms. Here, we just need to set B to be root n. As you can see here, using these techniques, you can do actually a dimension net reduction from n to root n. And note that in every iteration, one of the major computation we need to care is P times H. And therefore, we plug in a sketching matrix between P and H, and we need to add an error to control the error. Another way of compression is called vector maintenance. So there are 4 papers, and from last year to this year, all of them, their algorithms are stuck at n to the omega plus n to the plus 1 over 6. And all of the algorithms, they use slightly different techniques. Some of them using sketching, and some of them using sampling, and some of them using vector maintenance. As you can see, it's actually non-trivial to improve this 1 over 6 due to there are a lot of papers they actually use the same running time here. So one major idea of our algorithm is called lazy. And think of like you are giving a bunch of sequence of W and also H, and capital T is root n because you have root n iterations. And each iteration, you get like W, you need to compare, you can compare WT and WT plus 1. And what you can see is that they are going to be nearly sparse, and which means for most entries, their difference is tiny, and only a few entries, their difference is huge. And your goal is following. Whenever you see a W, you are going to output the letter C, and such that Vt minus Vt plus 1 is actually exactly sparse, because this is easier for you to do the sparse using sketching technique. The guarantees you need is you need to make sure f of Vt is roughly close to f of Wt for every t. Here, f can be many different things. For example, identity, and p, function p, or function p times h. So here I'd like to give you an example of how this laser algorithm working. So you should think of like this W is a dog and V is a human, and you are trying to walk in their dogs. So usually when you are trying to walk their dogs, you have a leash, and however there are limitations of leash length. You cannot hope every dog is like a left pitcher can take care of himself. For most of the times, you need to have a leash to take care of dogs to make sure the dog is not moving too far away. And you want to make sure like a dog or your kid is not lost and not hurt. And in the meanwhile, you also want to do something else. For example, getting a call on the phone, or like doing research, working on some papers. Here is the illustration. This is at the beginning, this is your dog location. And this blue circle is your human location. And what you need to do is, at the first step, you just set up the initial location to be the same. And when your dog moves, your human need to chase. But you don't need to stand at the same location as the dog again. You just need to make sure the leash is not breaking. And in the third step, when the dog moves again, at this time, human doesn't need to move. And in the fourth step, when dog moves again, at this time, human needs to move. You just keep doing this and so on. And after a lot of steps, and the dog is moving, your human is chasing. Eventually, if you draw the trails for all the dogs' moves, and also the trails for all the humans' moves, you can observe that the length of the blue lines will be much smaller than the length of the orange lines. That's how we improve running time. So here I will just give you a high-level idea what's the difference between the two algorithms. So in the 2019 algorithm, the major observation we have is we explore the changes are changing very slowly. And for example, when your dog is moving, human is chasing. In the new paper, we improve this equivalent from 2 plus 1 over 6 to 1 over 18. And we have some new observation, which is called the changes of the changes are changing very slowly. And therefore, you can design a multiple level chasing question where you can think of like your human is trying to take care of a kid, and kid is trying to take care of dogs. And there are three things they are chasing each other. And sometimes human move, sometimes kids move. And that's the high-level idea how we actually improve the running time. So overall, for all the VDS algorithm and the CLS algorithm and this year algorithm, all the algorithms they use routine iterations. And the major part different is the cost implementation is different. And in the CLS algorithm, you need to balance update time and query time for this blue A. And that's how you eventually get this n to the 2 plus 1 or 6. And in the new algorithm, we'll design some much more sophisticated complex data structure. And we need, in order to, instead of optimize one parameter, we need to optimize two parameters, both A and A tilde. And eventually, you can actually improve the equivalent from 1 over 6 to 1 over 18. So what I just presented is a mentioned multiplication time algorithm for LP. We use the changes slowly observation, and also we improve it. We use the observation changes of the changes are changing very slowly. In the rest of the talk, I will give you application of the technique. The first application is improve the training neural network. In theory, we can get into omega plus m times n. This algorithm is optimal. I will justify later. And the idea we use it, major idea we use is called interim sketching. In new layer submission, we use the idea from CLS, the slowly changes has been used slow changes, and also using lazy update idea, we can speed up training of neural network 6 times in practice while keeping the accuracy. Now I just finished the part of LP. I will go to deep learning. Deep learning has been shown has a lot of amazing performance in practice. For example, image classification. It also can do very well job in natural language processing. For example, translate the English to Chinese or translate the Chinese to English back. It also can be used in health and medical data. As a professional Go player when I was very young, and in a few years ago, I see this deep learning, I see AlphaGo build a system can be the human best player over the last decade. I was very shocking. And also recently, OpenAI has a system, they can build a deep learning system to play Dota, be the best Dota human player. One of the ultimate goal of deep learning is maybe like making an automatic driving system. For someone who doesn't know how to drive like me, you can still have your own car. As all of you can see, deep learning is the most powerful hammer in this century. It can be used for solving almost every question. But you may ask, is deep learning actually alchemy? I know that many of you may have different understanding or different opinion, but the major question I want to ask here is, do we actually understand deep learning? Do we understand the mysteries behind deep learning? Do we understand why it works very well? So in general, there are several ways to define machine from different levels. The first level is called calculation. And the second level is called memorization. And the third level is called, you can actually simulate some human intuition. And the fourth level is actually even stronger than human. However, my personal feeling, I'm not representing any of my co-author. I just want to share my personal story and my personal feeling about deep learning. My feeling is deep learning currently is doing something called memorization. So here is an example. For example, if human can play Go, as we all know, when I was very young, my coach taught me when human play Go, we should base on intuition. But does machine beat the human imply machine actually has intuition? Here are three Go bots from a same game played by Licedo and AlphaGo in 4 years ago. And these three bots, they are corresponding to the different stages of the Go playing. So the first stage is called the early stage, and where there are very few stones on the board, for example, less than 50. And the second stage is called middle stage, and where you have roughly 100 stones on the board. The last stage is called final stage, where you have almost 150 stones. I'm not sure if any of you know, like for the last stage, the machine can even build a human like 20 years ago. Because for the last stage, there are only very few choices you can do. And therefore, machine can just do something called brute force, can easily beat a human. However, the major challenging part is the first stage and the second stage, where deep mind overcome. Because the first stage requires something called intuition and memorization. Here you can think of memorization, the way you play Go is more like the way you do the T-set research. You just memorize how to use turn-on bound. However, knowing how to use turn-on bound is not enough to solve some problems. You still need some intuition to guide your research. And when I see deep learning, when I see AlphaGo system can beat the human, I was very shocking because I know human play Go based on intuition. Since AlphaGo can beat human, it may be indicating the AlphaGo or machine actually know what is it, can actually do something intuition now. That's very impressive. But however, I look at their paper, the way they do the intuition step is still based on some calculation and a neural network prediction and some pruning. Based on my opinion, they are not really doing intuition. Just the algorithm become better now. So one question you may ask is, if deep learning is already working well in practice, do we need to understand why? And here is the example. We see the birds flying on the sky. And what if we want to fly, should we just flip our arms? And the answer is no, because in order to build some aircraft, we cannot just flip our arms. We need to understand the science and mysteries behind birds flying. And then we can build some aircraft to improve our life and society. Over the last couple of years, between both my PhD time and post time, a lot of questions for deep learning bothers me. Therefore, I spend a lot of effort I'm trying to build a theory behind deep learning in order to give some guidance for better practice in the future. So here are some questions. It really bothers me a lot. For example, why SGD works very well for deep learning such a non-convex function? And how fast can we train the neural networks? And can we train the neural network in a secure way, for example, without revealing the original data? Here are my answers for part of those questions. I'm not claiming my answers to solve the problem completely, but I do believe those are very important first steps to eventually understand deep learning. In order to explain why deep learning works very well, we build some theory. For example, if you assume input image to have Gaussian, we can show SGD is converging. Also, in an open train regime, if you just assume neural net wide enough, you can also show it's converging. The next question is how fast can we train a neural network? And this is a major part of the rest of our talks. We have examples for both in theory, and then we generalize theory ideas in practice. The third question is, can we actually train neural network in a secure way without revealing the data? This is a major research I was doing while my postdoc time with my postdoc colleagues Kylie and Sanjeev Arora. We have some very practical training methods called insta-head and text-head. Those methods, they are working for both images and languages. Recently, we won the Bell Lab Prize for this method. The major idea of this method is very simple. You just need to change 2 lines of the way you train neural network in PyTorch or TensorFlow. The first thing you need to do is, instead of using original image, I'm selecting K images and to add them together. And this is motivated from some theory idea called sketching or sampling, where this is how you do a dimension reduction in general. And the second idea is, after you get the mixed image, you will just switch each pixel by half probability. This is motivated from the faster GL using Fourier transform, where you need the diagonal sum matrix. So in order to understand if our system is actually private in practice, I will also try to build some theory behind it, trying to attack the system, my system myself. And that's major motivation is all from some theoretical computer science problem. For example, batch K-sum or sparse matrix filtration. In the rest of the talk, I will focus on how fast can we train the networks. So one type of my research is I like to make things faster. So in the rest of the talk, I like to present 2 applications of my NLP techniques. The first one is from theory perspective. I will only talk about optimization. I will not talk about generalization. And for the second part, I will show how to generalize the theory ideas to practice. And I will show you a location where we can speed up the training, where we use the fully connected neural network in an NLP task, for example, BERT or transform. Here, I'd like to give you a setup of a deep learning training for just one hidden layer, a toy example. And on the left-hand side, you have a picture, and you want to design a neural network to learn if this is a dog or a cat. So the input layer has D side, which is D corresponding number of pixels, and the hidden layer has M nodes, and last layer has 1 node. In your classification, for example, MNIST, when you do a 10-class classification, we usually set up output layer to be 10. But now here, I just give a toy example. Once you have those data, your goal is you want to learn a function f, which is mapping from Rd to R. So D is the number of pixels in an image. And more specifically, you can say your function f can be written as this way. Here, AR is the width of the last layer, and WR is the width for the first layer, and phi is the ReLU active function. Of course, you can also consider about other active functions. Here, I just focus on ReLU. And for weight W1, it just means you look at the first hidden node in the hidden layer and look at the correspondence from all the input layer. And these are giving D numbers. These are formulating a vector W1 in D dimension. And then W2 is for the second hidden node. And W3 is for the third one. And you keep moving. And A is a vector in length M. And here M is the number of hidden neurons and also the weights of the neural network. And A are the corresponding weights. And here I just plot the W. One example in practice, we sometimes consider a fully connected neural network. In this case, you can think about capital W is a matrix by concatenating all the vectors for different hidden nodes. In order to train this neural network, you need to have something called loss function. The input of loss function is the weights of your neural network, which is A and W. And the loss function is very simple. You just look at the prediction of the neural network f of xi And also the corresponding label, it should have yi and take square, and this is called square L2 loss. And then you just do a gradient descent based on the loss up to W. This is how we train the neural network. In the rest of the talk, I will present the theory idea and practical idea to speed up neural net training based on this simple toy one hidden layer example. And our idea can be generalized multiple layer, but in the talk, I will just focus on one hidden layer. To implement our idea, I need a theoretical optimization framework for deep learning. So one reasonable framework is called overall penetrated framework. Here I just give you a brief introduction of this framework. This framework needs two assumptions. The first one is you need to assume all the input data they are separable. For example, the xi and xj, their L2 distance at least something. This assumption is a very, very reasonable assumption because in practice, if there are no image that is exactly the same. For any two images, their distance at least something. The second thing is called neural network need to be sufficiently wide. And here you should think of M is the number of neurons, and M should be at least a polynomial of all the parameters. Here N is the number of input data points, L is the number of layers, D is the number of pixels, and delta is the parameter of separability in the first assumption. So the major point is as long as M at least all the parameters, which means this is over penetrates neural network. The number of parameters of neural network is much larger than the input data. In this neural network, in a joint work with Alan Zhou and Li, and in 2019, we can show that starting from random initialization and with high probability, the stochastic gradient descent type algorithm is going to find a weight W such that the loss at W is at most epsilon in only roughly log 1 epsilon iterations. Intuitively, this math theorem is saying the following thing. If there are enough parameters in the network, then the greedy type algorithm training allows neural network to actually memorize the input data points. Therefore, this theorem we proved just another evidence. That's why I believe deep neural network is doing something called memorization. Here, let me recall you the basic setup of one hidden layer again, and in order to introduce my theory result. N is the number of data points, and D is the number of pixels in image. For ease of thinking, let's say D is constant. And M is the number of neurons, also the width of a neural network. T is the iterations. And instead of compare the major difference between LP and neural network is LP, the capital T, is root N. Here, it's just log N over epsilon. So C is the input parameter size, which is equal to the input points plus parameter of neural networks. The input of number of data points is O of ND, which is O of N. Usually think of D as constant. The number of parameters in the neural network is MD plus M, which is O of M for constant D. Although the parameters is only M plus N, however, in order to evaluate at N points for the neural network, you need to take O of Mn time. So here in theory, we provide a second order algorithm. So I want to mention that this second algorithm in practical deep learning, we don't use the second order algorithm, we only use first one. We only use the first order. But I would say like this second order algorithm is a very important first step to understand how should we speed up deep learning in theory and practice. So naive implementation of the algorithm will take n squared time plus n to the omega. Our clever implementation takes only mn plus n omega. And our algorithm is actually tight. I will justify why in a later slide. Here I will say like one of the very interesting questions in theory for deep learning is can we actually train the deep learning network in the matrix multiplication time? As we all know for LP, we can solve it in the matrix multiplication time for now. But what about deep neural network, such non-convex optimization? Recall our LP result, which is n to the 2 plus 1 was 18 plus n to the omega. And n to the 2 plus 1 over 18 is less than omega, since our current omega is roughly 2.3. However, our deep learning result is mn plus n to the omega. So here is something different. In LP, the first result is smaller, but in current deep learning theory, the first result is actually larger. Because if you want to make sure the open insurance theorem work, you need m at least n to the 4. This is due to a paper with my co-author Xinyang. So here I would like to justify why our deep learning theory result is optimal. First, even you want to inverting an n by n matrix, this takes already n to omega time. This gives you a justification why the second term is tight. Second, even like you want to evaluate an endpoints in this with m neural network, you have to take it has span mn time. Therefore, mn is a theoretical lower bound. However, what about practice? So another interesting question in practice is, we know in theory, mn plus n omega is the best thing you can hope, but in practice, because data they are not worst case, is there some trick or any ideas we can hope don't spend mn time per iteration? In the next few slides, I will show you my practical work. Here, let me remind you the neural network again. You have one hidden neural network, and on the left-hand side, you have a picture as a dog or a cat, and you want to know if it is a dog or a cat. And one of the major observations we have is for any data xi, if we want to compute your evaluation of the neural network f of xi, this step already takes m time because you have m terms. For even using a d constant, this step takes m time. The major observation we have in practice is only a few number of neurons matters. Say like instead of adding m neurons scatter, you only need to add a subset of them, which is si. For example, you just need to operate this estimator, and then you can actually give a good estimation of your true estimator. The major point of the major property you have for this set si is for any r in this si, wr times this xi at least something epsilon. So here is the example. What you can, in order to check which si set is bigger or small, you can just compute the inner product between the image and this w1. Then you will know, for example, for the first neuron, the entry is small, and the second neuron entry is big, and the third one is small, and then it's small, and the last one is big. Therefore, after you compute all this inner product, and you will see only the second neuron and the last neuron are matters. They are your green set Si. Therefore, you can just compute the output layer. But there is a problem for this method, because what I'm doing is I'm basically computing all the neurons. Compute each neuron, you need to spend d time, their m neurons. So the question is, naively, it takes md time. Can we beat this? Can we get some sublinear in m? Because you need to eventually evaluate endpoints. If every point you still spend m time, eventually you are still not good. The major question is, how do we figure out this set Si in sublinear in md time in practice without computing the inner product directly? So this idea is in a clear summation. And what we do is the following. At the beginning, we have all the weights of the neural network. We will pre-process all the weights and build a near neighbor search data structure, say like LSH, locality sensor hashing. And we initialize the data structure with all the weights. And in the future, whenever I see xi, I will just do a nearest query, and with another parameter called k, and k is going to return me the top k nearest neighbor. Because I'm assuming all the data points, their L2 norm is 1, therefore the inner product is correlated to the L2 distance. You can just use the L2 nearest neighbor search data structure. But there is still a problem, even you can build this data structure. The point is every iteration, Wt plus 1, is changes from Wt. If we rebuild data structure every iteration, this is still too expensive. You cannot afford to do this in practice. You still cannot do some speed up. And however, what we learn from LP algorithm is we can do something called lazy. Because Wt plus 1 is changing very slowly from Wt. Therefore, you don't need to update the entire data structure. And then like what happens is, what if we apply the idea to training? And for example, a fully connected neural network in LP task. We call our method is called some mongols. This is some animals. And one of the major properties of these animals is they are very lazy. That's why we choose this animal to name our method. So here is some practical experiments I like to show off all of you. And the first column is our data sets. First, they are all like NLP language data sets. This is doing some multiple label classification thing. And there are 2 data sets from Wiki and also Amazon and also Delicious. And the second and third columns, they are corresponding to accuracy and times where you spend the full computation without using any smart thing. Just every time you compute the fully connected network and compute all the neurons. And the last 2 columns is our method performance. As you can see, all the 4 rows for different data sets, the 2 algorithms accuracy, they are almost the same. However, if you look at running time, we can actually have a lot of speed up. For the Amazon data set, we can actually have 6 times speed up. So here I like to discuss something in the future. As we know, LP can solve into the n omega plus 2 plus 1 over 6. We use some idea, we put something called the changes are changing very slowly. Recently, we improved 1 over 6 to 1 over 18. And we put some idea called changes of the changes are changing very slowly. In this clear summation, we use the idea from the CLS, which is the changes are changing slowly. And then we can speed up training in 6 times while keeping the prior accuracy. And in the future, I would plan to try the idea in my new LP paper, which has observation the changes of the changes are changing slowly. So the question is there a chance we can speed up further more, for example, 18 times. Here I would like to thank all my co-authors, and without all of them, I cannot afford to write all these papers and all this research. And finally, I'd like to thank all of you for attending this talk, and feel free to ask any questions and also provide any suggestions. Your comments are very important for me to finding jobs. And also, none of my affiliation emails somehow are not working. Yeah, so if you have any questions for the slides or the talk, I would very appreciate it. Please email to my Gmail. Thank you.
So any questions? This one question that I had is, so there are a couple times it appeared you talked about this lazy updating trick that you can do.
Yeah.
Is there a way that you can formalize what you need so that people could like work directly on that as a data structures question?
Oh yeah. In this clear submission, we are trying to like make this thing more general, because in previous papers we just focus on LP or focus on other particular questions, and in this clear submission, we are trying to. I wouldn't say we have a new data. I wouldn't say we have a complete framework, but our current framework, we are trying to fit the nearest neighbor search data structure with our framework. And before we just focus on the matrix vector multiplication or matrix multiplication, but now we are trying to concatenate with this our idea with nearest neighbor search. Yeah, we are still trying to think about a better way to actually formalize the idea. Currently, we don't have a real framework to fit everything. We still need to do some hand calculation and modification for different problems.
Mm-hmm. Okay, so the question I had is, so in the experiments you do, what is the network there?
Yeah, here I would like to justify, I'm not claiming my technique is fundamentally changing the deep learning training. And so currently the idea is used for some fully connected neural network, which is widely used in NLP task, in natural language processing. As we know, like in image.
In NLP, this is a state-of-the-art network?
Yeah, because they use some BERT or like a reformer or transformer, they do have a fully connected layer somehow.
Mm-hmm.
And that fully connected is very large because they need to compare the attention between all the words. And yeah, that's we try to like generalize idea for some other neural network, but we are still working on, yeah. But currently, the NLP task is easier to show this idea.
Mm-hmm. So like, if I want to do state-of-the-art training, that is what I would see your left column.
Yeah, I think so, yeah.
Cool. So any questions from anyone else?
I had a quick question about something you mentioned when talking about linear programming. So you said at the moment it is a bit more difficult to solve linear programming than solving linear systems, but you believe that these should be the same level of difficulty. And I wonder why that is the case. Why should solving LPs be as easy as that?
Okay, so when I write like those let me go to one slide. Sorry. Yeah, here. So when I write this first paper n to the omega plus n to the 1 plus 1/6, I think we just want to get an algorithm which is for the current n to omega. We never try to optimize this 1/6. At that time, I do believe like LP solver should be eventually only dependent on 2 omega without any additive terms. But after I tried a lot of ideas, as you can see, like in previous slides, I wrote many papers. Even just repeat this 2 plus 1/6 is already very hard. So use some other ideas. And currently, the best we can do is n to the 2 plus 1/18. Yeah, currently, if you ask me this question like 3 months early, I will tell you I definitely believe LP can be as hard as fast as a linear system. But right now, like for the last 2 years, I spend a majority of my time trying to improve this 1/16 and 1/6, 1/18 and 1/6. I kind of really stuck. I almost tried there like 100 methods, like so many pages of calculations, and currently I'm truly stuck. I would be very surprised if someone can improve my paper, to be honest, and I don't have any idea how to improve my paper right now, and therefore I still more likely intending to believe they are going to eventually have the same running time, but I don't know the answer for now. Yeah, and also for linear system, and there are no point, there are no way you should believe it takes n to the 2 plus some time, because currently we don't know any lower bound, super quadratic lower bound for matrix multiplication. Therefore, like yeah, unless we know some better lower bound for matrix multiplication, but that's unlikely to be true because this question has been thinking for a long time, many decades. So yeah.
Right. Well, you actually mentioned this lower bound due to Ron Roth, which is like n squared log n or something,
Yeah.
right?
Yeah, and also that's only for some specific, very special computation model, which is not the European.
Right. I was going to ask that. It looks like that's for some sort of arithmetic circuit model.
Yeah, exactly.
Not for. Right.
Yeah.
Okay, so there's no like lower bound better than quadratic time known in some more general model.
So one thing I like to mention is usually in order to like speed up the matrix multiplication, the question is boils down to design some tensors, and which is give you a smart way to group all the matrices, and that's how you can fast multiply them. And so far, the best tensors, all the tensors we know on the Earth, they cannot go beyond the 2 plus 1/6. So if you need really improve the running time from like even 2.3 to 2.16, you need some fundamental new idea. And there are some like conditional type of lower bound, not like it's very like a condition. It's more like saying some specific method is not working. It's not a general lower bound. But that's somehow known for super quadratic. Yeah.
All right, can someone put the Gather.town link